Hi everybody, and welcome to part 4 of a 5-part webinar series teaching you everything you need to know about thermal imaging drones and the solar industry. Today's topic is limitations of thermal drone inspections. My name is Brett Conda, and I'm joined by my co-host Austin Coffin, Head of Sales for Raptor Maps. During this webinar, we're going to discuss the following topics: camera limitations, environmental limitations, irradiance and operating status, coverage and flight times, and we'll wrap up with a conclusion. So before we start, we've had a common theme throughout these videos, and that is to start with the end deliverable and the end product and work your way backwards. So if you're looking for a high-level qualitative analysis, you need to take one approach. If you're looking for a high-resolution 3-centimeter ground sampling distance project, you're going to need to take another approach. So Austin, how does the camera actually affect your deliverables when we talk about this methodology and approach that we're talking about here?
In short, the camera affects the resolution that you are able to capture, and that directly affects what types of anomalies can be detected. So when we talk about resolutions, 3 centimeter per pixel, 5 centimeter per pixel, and 15 centimeter per pixel are what we here at Raptor are standardized on. It's also what we see globally people standardizing on. Each resolution is really focused on a different reason to be out there and a different end goal of the inspection. And that also relates to, the frame rates, lens size. But a 13 millimeter camera going out there to find cell level issues, needs to really be flown at 120 feet altitude, we'll say, which will deliver a 5 centimeter resolution, which will allow you to correctly identify cell issues. If you fly much higher, you're limited in what you can correctly identify.
Thanks, Austin. And the next topic is digital versus thermal zoom. Many of you are going to be flying dual sensor EO/IR cameras. You need to realize that when you see 5x zoom, that's actually the optical sensor that's doing the zoom and not the thermal. So the thermal image is not actually zooming and maintaining those pixels on target. Also, reflectivity is a really important topic to discuss because solar and PV modules tend to be highly reflective, which lowers its emissivity, and that can also affect your data and your image quality. So understand that PV modules are highly reflective, and therefore the emissivity needs to be taken into consideration before flight. So we have two images here, one on the right that is taken by a high resolution 640 by 512 camera. Image on the left is a lower resolution 160 by 120 resolution camera flown at 75 feet. So Austin, this is a great representation of what we can see in a solar field, but take us through these images and exactly what we're seeing and how it relates to inspecting a solar panel.
So I believe in both images, the hotspot is a 12-inch diameter metal pan that's been heated up. Fun fact, this metal pan is actually, I'd say, twice as wide as the average solar cell that is in a solar panel. So this is a good example. And as you see on the left, the image is very blurry. It's not really the highest quality image of the quote-unquote anomaly. On the right, much clearer. There's a lot more pixels making up that hotspot. And I actually believe it's probably, I think, about 4.3 centimeter per pixel ground sample distance for the picture on the right, based on the frame and the lens capabilities. But in short, this directly correlates to you have to fly at the right altitude to correctly identify an issue. And if we're talking about solar inspections, the image on the left from the last slide and this slide, not flown at the correct altitude with the type of equipment. On the right here, in this second slide, you can see that this hotspot is still fairly easy to identify, although the GSD is 11 to probably 11.5 from what I can see here. And once again, if we were looking to identify a 12-inch diameter issue on a solar module, then we could correctly identify it in this picture, which means we can actually fly 200 feet. But on the left, it's not even visible, which means you're flying way too high and you're missing a lot of what you're trying to find if the goal is to find a 12-inch diameter issue.
Those types of images are very telling, and another factor that's going to affect that resolution is environmental conditions. We touch on this in other videos, but you need to realize that atmospheric transmission is happening between the camera and the target, and the more atmosphere that is between the camera and the target, the higher the possibility for absorbing and emitting infrared radiation. So air density, relative humidity, distance to target, these are all conditions and issues that are going to affect your resolution and ultimately your ground sampling distance. So not accounting for these factors leads to radiometric measurements that might appear cooler at the end of the day if your goal is to produce radiometric data. So Austin, what are the other environmental limitations that are going to affect your ground sampling distance and are going to affect your ability to fly?
There's a lot of things, as you covered, but rain, having any sort of rain at the site that you're inspecting before you are heading out there, or as you start to inspect, rain is going to essentially completely ruin the day for you because you can't capture thermal imagery of a solar farm when there's water on the modules. Clouds are going to dramatically affect the production of the site and the irradiance level of the site, which means that once again, thermal cameras are going to be dramatically impacted on their ability to pick up on the anomalies that are present in the site based on the irradiance level of the solar site. Moisture will have an impact on the thermal camera, as I believe we've talked about in the past, but that is a limitation that you can make adjustments for in the camera settings. And wind and high winds are going to affect the clarity of the image. It's going to result in blurry images. It's going to result in low quality images that are going to be hard to correctly identify anomalies. And winds are also going to dramatically affect a lighter drone than a heavier drone. But on average, I believe, winds over 10, 15 miles per hour are probably kind of that threshold where under you're fine, but once they hit over 15, the images can really just come out terrible.
And rain and moisture on the ground tends to make the temperature uniform. So that's the issue there, is that moisture on top of the cell is going to make everything look the same temperature. So Austin, what is the best type of irradiance to fly, and go over what exactly irradiance is for our viewers?
Irradiance is really just the density of radiation that is on the surface of the module itself. And 600 watts per meter squared is the global standard from what we have seen, from what we have heard and seen also in requirement documents and the data collection. 600 watts per meter squared is really that threshold where anything under it, you're getting into a gray area where you may not be able to identify or capture imagery of anomalies. Over that, and it's great. The farther you go over 600 watts per meter squared, it doesn't impact anything. It just means that it's better radiance, and maybe the images are a little more clear. But that is also directly relates to cloud coverage. So when there's a cloudy day, the irradiance will drop lower, which means that you're out there flying around and no anomalies are being identified or picked up by the images. And I think that's where this kind of graph or image on the right here does a good job of visually showing you when you're on site, if it's a clear sky day or if it's a cloudy day, you'll see how that can affect the irradiance.
And as Austin mentioned, the standard for irradiance to properly inspect solar panels is 600 watts per meter squared. At that irradiance, that is the optimal time to go out and fly. It's still possible to inspect at a lower irradiance, but the anomalies are going to be more difficult to identify. So the lower the irradiance, the lower the odds are of you finding cell level anomalies. Austin, go over more about coverage and how it affects your data.
So coverage is a very popular question that I get a lot, and there's a lot of factors that impact coverage and the limitations of the drone's ability to cover a certain amount of space. The camera equipment, the specs of the camera, the size of the solar farm, the altitude that you'll be inspecting the site at, the resolution requirements, all of these go into play. So it's not just a black and white answer. And then also the overlaps, how the drone itself is flown. So with Raptor Map software, it's a very low overlap requirement, which means it's only 80 by 20 on the overlap, so 80 front, 20 side. And what that means is you cover more ground in less time than with your traditional mapping overlaps of 85, 85, or 90, 90. You get sites done 400% faster, at least, and 80% less data is captured, which means that you can cover more ground. But when you put on resolution requirements that are 3 centimeter resolution, you have to drop the altitude down. That slows down how much ground can be covered in a single flight, which means it slows down how much solar farm can be inspected in a single day. And then when we talk about flight times, once again, how fast the drone can fly directly correlates to how high and low the drone is in the air. And also the overlaps, again, are going to really affect the flight times in the wind and environmental conditions. But I think in ideal conditions where the solar farm is at the rate of radiance of 600 watts per meter squared, on a great, beautiful summer day, you really only have maybe 6, 7, 8 hours total to do your thermal inspection, because you can't start too early and you have to end earlier in the afternoon as the irradiance drops. And this is why something like using multiple drones on these sites is a really valuable tool, because one drone can only cover so much. And if you have a larger site and you can safely operate 2, 3, 4 drones on these massive utility scale sites, you can complete the inspection in a single day or a couple of days. And I would say that this is a great opportunity to reduce risk within the inspection, because the risks involve environmental conditions, equipment failures, et cetera, and getting the job done faster is the best thing you can do. You can move on to the next job. The client gets the data sets and the deliverables faster. And at the end of the day, if something was to happen tomorrow, it doesn't matter because you've already completed the job.
And the average multi-rotor flight time is about 30 minutes. And, there's new technologies that are being developed for the drone industry every day. We're seeing things like hydrogen cell fuel cells that are increasing flight times to an hour and a half, 2 hours. Most fixed wing platforms have that level of endurance of an hour and a half, 2 hours. But when you are flying that length of time, you need to remember that current regulations restrict you from flying beyond visual line of sight. So unless you have a BVLOS waiver, make sure you can always keep that drone in sight, but fly for as long as you'd like. So to wrap up here, understanding resolution requirements early on is going to help you to properly plan your missions. Take the end deliverable and work backwards. Thermal imaging drones are not always the solution for every scenario. PV fields must be the proper irradiance to accurately find anomalies, and that irradiance is 600 watts per meter squared. The hardware, altitude, and overlap are the main factors contributing to time on site and how many acres you can cover in a day. And as Austin just mentioned, we suggest flying multiple drones to maximize efficiency. So Austin, as always, thank you for your time, for your expertise. These videos can be found on the FLIR Delta website, and we'll see you next time.